All right, let's dive into one of the coolest and most powerful ideas in all of machine learning. It's a simple concept. A team of AIs working together is almost always way smarter than one single genius AI working alone. So, to really get how that works, let's start with a question.
So think about it. You've got a really tough decision to make. What's the better play here? Do you go with the advice of one certified genius, or do you pull a big group of pretty smart, well-informed people?
Well, going with the genius is definitely high risk, high reward, right? They could be absolutely brilliant, or they could be spectacularly wrong. The crowd, on the other hand, is just safer. There's this wisdom of the crowd effect, where everyone's individual mistakes, their little biases, they all tend to cancel each other out. And what you're left with is a much more reliable, stable answer. This exact idea is at the very heart of what we're talking about today.
And that brings us to the main event, how we harness the wisdom of a machine crowd. The technique is called ensemble learning. So what is it exactly? Well, to put it simply, ensemble learning is all about combining the predictions from a bunch of different machine learning models. The whole goal is to create one final prediction that's way more accurate than any of the individual models could ever be on their own. So instead of trying to build one giant, perfect, super complex model, you build an army of smaller, simpler ones.
But here's the key, and this is absolutely crucial. It's all about diversity. Just like a human team is stronger when you have people with different viewpoints, an ensemble works best when its models are all a little different. You actually want them to attack the problem from different angles and make different kinds of mistakes. That way, when you bring all their opinions together, those errors just fade away.
Okay, so let's check out the first major strategy for building these AI teams. It's called bagging, and you can think of it as the parallel team strategy.
So here's how bagging works. First up, you take your main data set and you create a whole bunch of smaller, random samples from it. This process has a name, bootstrap sampling. Step 2, you train a separate model on each one of those little data samples. And importantly, this is all happening at the exact same time, in parallel. Then finally, you just combine all their predictions. For a yes or no type question, you take a vote. For predicting a number, you just average their answers. Simple as that.
Now, the big win with bagging is that it cuts down on something called variance. Just think of variance as how much a model freaks out over tiny, random noise in the data. By averaging a bunch of models, bagging makes the final result much more stable and robust. And this helps prevent a classic machine learning problem called overfitting. That's where a model gets so obsessed with the training data, it can't handle anything new. The most famous example of bagging in action, that would be the random forest algorithm.
All right, on to our next strategy, boosting. Now, if bagging is like a team working in parallel, think of boosting as the sequential team. See, bagging is great, but all the models are trained independently, kind of in their own little bubbles. But what if each new model could actually learn from the mistakes of the one that came right before it?
And you can really see the difference here. On the left, you've got bagging, where everything happens at once. But on the right, you have boosting, and it's sequential. It's a chain. The first model makes its best guess. The second model then comes in and pays extra attention to everything the first one got wrong, trying to fix those specific errors. Then the third model focuses on what the second one missed, and so on, with each one getting progressively smarter.
The huge benefit here is that boosting reduces bias. Bias is basically when a model has these flawed, built-in assumptions that cause it to consistently make the same kind of error. By obsessively focusing on its mistakes, boosting creates a final model that's incredibly accurate. It just slowly but surely zeroes in on the right answer. Some famous examples you might have heard of are AdaBoost and the real powerhouse gradient boosting machines, or GBMs.
Okay, so we've seen a parallel team and a sequential team. Now it's time to meet the ultimate team manager, stacking. This is all about bringing together a bunch of different, already powerful models.
Stacking happens in 2 layers. On level 0, you don't just use a bunch of the same kind of model. No, you assemble a diverse team of heavy hitters. So you might have a random forest, a gradient boosting machine, and maybe a support vector machine, another really strong technique, all looking at the exact same problem, but from their own unique perspective.
And then comes level 1. This is where the magic happens. You introduce a new model called a meta-learner. And this is just brilliant. This model doesn't look at the original data at all. Its training data is the predictions from your level 0 team of experts. Its entire job is to learn the strengths and weaknesses of each expert and figure out the absolute best way to combine their answers to get the final best prediction.
This incredibly powerful idea has actually been around for a while. It first popped up back in 1992 was made more formal in '96 and finally got its theoretical legs under it and that awesome name superlearner around 2007.
But for years, even though people knew stacking worked, and worked really, really well, nobody could quite prove why. As this quote says, it was basically considered a black art. People knew it was this amazing trick that kept winning machine learning competitions, but the math behind how that meta-learner so cleverly weighed the expert opinions, that was a mystery.
Okay, so we've got these three really powerful strategies, but let's bring this out of the world of theory. Why does any of this matter in the real world?
Here's a quick little cheat sheet to pull it all together for you. Bagging. That's our parallel team. Its main job is to reduce variance and make models more stable. Boosting. Our sequential team. It learns from mistakes to reduce bias and make models super accurate. And finally, stacking. The team manager, using a meta model to get the absolute maximum performance out of a diverse team.
And you might be thinking, these sound like they're just squeezing out tiny improvements. But in a lot of high-stakes situations, even a 1% boost in accuracy is a total game changer. In finance, that could be millions of dollars. In medicine, it could mean saving lives. And that game-changing impact is exactly why you see ensembles everywhere in critical fields. They're at the core of fraud detection systems, they're used to spot malware and computer intrusions, they help doctors make diagnoses, and they power high-stakes financial trading. In any area where accuracy and reliability are non-negotiable, ensembles are king.
Which kind of leaves us with one last big thought to chew on. As we keep building more and more powerful AI, maybe our best safety net isn't trying to create a single, perfect, super intelligent AI. Maybe, just maybe, our best bet is to build a diverse, robust team of them, where the wisdom of the machine crowd ensures that no single point of failure can ever lead us astray.